Have you ever really looked at a diamond and thought about that phrase, a diamond is forever? I mean, it's just carbon, right? The exact same stuff that makes up the graphite in your pencil. So what's the deal? What's stopping every diamond from just poof, turning into a pile of pencil dust? Well, that question takes us right into the fascinating hidden world of chemical speed. So look at this. On the left, you've got a diamond. It's one of the hardest, most valuable materials we know. And on the right, graphite. It's so soft you can literally write with it. They look different, they feel different, and they are valued very differently. And yet, believe it or not, chemically, they are identical twins. Both are just pure carbon. So, what gives? And here's where it gets really weird. The fundamental laws of chemistry, what we call thermodynamics, they say that graphite is actually the more stable, happier state for carbon to be in. That means, in theory, every single diamond on Earth is in a constant state of wanting to become graphite. So why isn't it happening? Why isn't your ring turning into a smudge? The answer, it turns out, isn't about if a diamond will change, but all about how fast. This is where we get into the difference between what's possible and what's actually practical. And it all comes down to two big competing ideas in chemistry. Okay, think of it like this. Thermodynamics, that's the part of chemistry that asks if a reaction can happen. It looks at the beginning and the end and says, yep, that's possible. But you know what? Kinetics is the real boss here. Kinetics asks the most important question. Okay, but how fast is it going to happen? It's the science of speed, and it's the entire reason that diamond is still a diamond. To really get how this works, you have to imagine something. For pretty much any chemical reaction to happen, it doesn't just go from point A to point B. First, it has to climb over a huge invisible hill. So check this out. Even for a reaction that ultimately releases energy, like a diamond turning into graphite, the atoms can't just slide down into that more stable state. Nope. First, they have to get a massive push of energy to get over this energy hill. That push is the energy you need to start breaking those incredibly strong bonds holding the diamond together before they can even think about reforming as graphite. And that energy hill has a proper name. It's called activation energy. Now, for a diamond to turn into graphite, that hill isn't just a hill. It's a colossal mountain. I mean, we're talking Mount Everest level colossal. The energy required is so immense that at normal everyday temperatures, the reaction is practically frozen solid. We're talking a timescale of billions, maybe trillions of years. So yeah, your diamond isn't changing because it's completely stuck at the bottom of an impossibly high mountain. But okay, what if we actually want to control the speed of a reaction? What if we want to hit the gas pedal or maybe slam on the brakes? Well, it turns out chemistry gives us a few different levers we can pull to do exactly that. There are four main things that act like speed controls for a reaction: how concentrated the stuff is, its surface area, the temperature, and a really cool thing called a catalyst. First up, concentration. This one's pretty intuitive, right? The more molecules you cram into a space, the more often they're going to bump into each other. More collisions means more chances for a reaction to actually happen. It's just like walking through a crowded room versus an empty one. You're going to bump into way more people in the crowd. Next up, surface area. Now, for a solid, reactions can only happen on the outside layer. But if you crush that solid into a powder, you expose way more surface for other molecules to get to. Think about it. A sugar cube dissolves kind of slowly, but powdered sugar disappears almost instantly. Or for a more dramatic example, aluminum powder is literally explosive in fireworks, but a solid chunk of aluminum just sits there. That's the power of surface area. Temperature is a huge one. As this graph shows, when the temperature goes up, the reaction rate just skyrockets. And why is that? Well, heat is just energy. When you heat molecules up, you make them move faster and hit each other harder. That gives way more of them the energy they need to make it over that activation hill we were talking about. And our last lever is one of the most powerful, the catalyst. See that dotted green line on the graph? A catalyst is like a chemical matchmaker. It doesn't actually get used up in the reaction, but what it does is provide an entirely new, easier pathway. It's like a secret shortcut with a much smaller energy hill. Catalysts make the impossible possible. So that's the theory. But this is not just some abstract thought experiment. The story of mastering chemical speed is in a lot of ways the story of how we built our modern world. You know, this understanding didn't just appear overnight. It was built piece by piece, over decades. It started way back in the 1850s, with scientists just measuring how fast sugar changed. Then came the laws that connected concentration to speed. And finally, the big aha moment came from Arrhenius, who gave us that crucial idea of the energy barrier, which was all explained later by collision theory. And this stuff matters because we use our knowledge of kinetics to control basically everything. We use catalysts to speed up how we refine gasoline, and we also use them in our car's catalytic converter to quickly get rid of toxic fumes. We slow down the kinetics of food spoilage by sticking it in the fridge. Mastering chemical speed is absolutely all around us. Which, of course, brings us to today. Our ability to control chemical speed is about to take another gigantic leap forward, and this time it's being powered by computers and artificial intelligence. Think about trying to design something insanely complex, like a new jet engine. Inside that thing, thousands of chemical reactions are all happening at once. To simulate all of that accurately requires an unbelievable amount of computing power. So much, in fact, that a truly detailed model would just be too slow to be useful for engineers. This graph really shows the problem. It's a classic trade-off. On one hand, you can have super detailed models that are very accurate and they have high fidelity, but they are incredibly slow to run. On the other hand, you can simplify them to make them faster, but then you lose a ton of accuracy. It always seems like you have to choose. Do you want it fast or do you want it right? So how do you get both? And the solution is to bring in machine learning. Scientists are now training AI to create what they call compact models. Now, these aren't trying to perfectly simulate every single little reaction. Instead, they are super efficient models that are trained to predict the correct outcome, giving engineers that perfect balance of speed and accuracy that they desperately need. And that brings us right back to the beginning. We started with a reaction that nature makes impossibly slow, a diamond turning to graphite, and we've ended up with a technology that lets us precisely model and control thousands of reactions happening inside a jet engine in a fraction of a second. This growing power we have over the speed of chemistry leaves you with a really big question. What other impossible reactions today will become perfectly controllable and maybe even commonplace tomorrow?